So that is what we are trying to put up here. You can see that within the flame zone, fuel from the jet side diffuses towards the flame zone, and predominantly due to concentration gradient and temperature gradient. At the flame zone, the fuel is consumed. That means at the flame zone where the maximum temperature occurs, where the products are formed, the fuel is consumed. Okay, I am saying almost completely, keeping in mind some small leak which may happen. Okay, because of finiteness in the flame zone, finiteness in the flame thickness basically. Okay, now similarly oxidizer from the ambient diffuses from the outer side, the ambient towards the flame zone, and it is consumed almost completely in the flame zone like fuel. So that is what is depicted here. You can see that almost consumed. Okay, it is not like exact 0. Okay, this is fuel and oxygen. It is not an exact 0 here. It will be like this. Small leak will be there. Some thickness. So if it is exact 0 like this, then the flame will have 0 thickness here like this, so 0 thickness. But if it is like not exact 0, but it goes 0 slightly away from this. So this is the point what I am plotting. This is the point phi equal to 1, but towards the phi less than 1 side or phi greater than 1 side also you can see some small amount of oxygen coming into the flame slightly and fuel going outside the flame slightly. Anyway, there will be so this is a very small thickness, finite thickness, say 1 mm or 2 mm, something like that, order of that mm, which is important due to the finite rate chemistry. But if you assume an infinite rate chemistry, then it will have 0 thickness exactly at this flame zone or phi equal to 1, which is indicated as phi equal to 1, the oxygen go to 0, fuel will go to 0 straight away. So this is the difference in this, but predominantly we can say that almost all the fuel is consumed at the flame zone and the oxygen is consumed at the flame zone. Small leak of both fuel and oxidizer is formed due to the finite rate chemistry basically. Okay. Similarly, products are formed at the flame zone and diffuse towards both the jet and the ambient sides. Okay. So that is also the product is also convected inside in the axial direction in the jet side basically. So this is very important to understand the profile within the flame. Now at the tip, okay, at the flame tip, what happens? Fuel does not exist because all the fuel is now consumed. When the particular flame tip is actually characterized by YF equal to YF stoichiometry. That means when you ignite this, the fuel has to, whatever fuel left there in stoichiometric proportion has to be consumed for the flame to be formed there. So fuel will not be there. Okay. So it means that fuel has travelled up to this point in the axial direction and has been completely consumed at the flame tip. So here you can see that when you draw profile at this tip, flame tip, in the species side you will not have fuel. Products are formed and they are the maximum at the center line and they decay. Similarly, oxygen, which is required for the combustion to take place at the flame tip, comes and goes to 0 at the axis. So oxygen from the ambient diffuses and goes to 0 at the radius equal to 0, that is axis. Okay. Temperature is maximum at the flame tip and decreases towards the ambient. So the profile is actually different. So you can see that this is the profile what you get. So local maximum at non-zero radius and reduction after that. So in the profile which exhibit for the products and temperature, but the temperature here maximum at the axis and decreasing towards the ambient temperature. So that is the profiles are little bit different. Even the products, you can see products are maximum at the flame tip at the axis, but the products are not maximum at the axis, they are maximum at the non-zero radius. Okay. Okay, so that is the thing. So again the oxygen going to 0 is not at the R equal to 0 here within the flame, but here it is exactly at the R equal to 0. So this is the structure. So the structure of this within the flame, you can plot structure. A representative structure at any axial location is enough. but you have to understand that this is not going to be the same at all the oxygen locations. There will be variations in the maximum values as well as the location at which the maximum occurs. And the flame tip is exactly different. Actually, flame tip you can see the maximum of temperature, maximum of product mass fractions occurring at the axial line itself. So this is the important aspect of the diffusion flame structure. Okay. So now at the flame tip, required oxygen has come from the ambient, seen from the radial profile, and it goes to 0 at the axial location, that is the axis. Then temperature reaches its maximum value at the flame tip, okay, and at the axis it is maximum, and decreases in the radial direction. Asymptotic reaches the ambient temperature value. Products are formed at the flame tip, diffuses towards oxygen. There is no flame, there is no inner zone at the flame tip. So these are the important aspects of the structure at the flame tip. So we have seen the structure within the flame and at the flame tip. Okay, now as I told you, very important characteristic of a diffusion flame is the visible length or the height of the diffusion flame. That is very important. So that how to calculate. Okay, so diffusion flame is characterized by the visible length. Okay, now we will try to do a simple scaling analysis. Simple scaling analysis to understand the it is not going to reveal the exact value of the flame height, but it will give us an understanding of the factors which are going to affect the length of the diffusion flame. Okay, that is what we are going to see now. Okay, now in this analysis we have to understand that predominantly in any diffusion flame the reaction rates are much higher than the rates of diffusion or the convection. Okay, so leave alone the turbulent regime, there are some complexities are there. In the laminar regime, basically the convection process are not due to very high velocities. So convection time scales and diffusion time scales, if you take chemical time scales are much smaller than that. So that means the reaction rates are much higher than the transport processes. So that we have already discussed several times. That to emphasize, I am again writing this. So as a result, the reaction zone will have a almost 0 thickness. That is what we are. So that finite thickness of the reaction zone is not considered here. When you go for the premix flame, the flame speed and the flame thickness, these are important characteristics what we saw. So the flame thickness was the characteristics. So here we need not worry about the flame thickness, take the flame thickness as 0 thickness because the reaction rates are much fast, infinitely fast. That is the important point here you want to have here. So now that means that we do not really care about the reaction rates at all, even you do not need a single step chemistry also. Just do it with normal non-reacting flow or simple chemical reaction system and so on. Just solve the without any source terms, you can solve the equations. Okay, now again another point which I am stressing here is the diffusion is predominant in the radial direction because there is no convection in this direction. Convection is present, the convection time scales are basically lower. So convection occurs in the axial direction because there is a initiation there from the port exit. So convection occurs from the axial direction, and in the radial direction it is predominantly molecular diffusion. Okay, now let us understand how we are going to do the analysis. So let us take the say some port from which fuel is supplied. Okay, now so there is a flame which is formed. So this is a flame which is formed. Okay, so only fuel is coming out and air entrains from the atmosphere, and you have reaction zone which is formed, which we have discussed. Okay, this is the flame zone which is formed. Now let us take a this is the axis. As the axis, let us take a molecule, fuel molecule. Okay, the fuel molecule goes to the radius here and consumes. So the fuel from the central line has to travel a distance in the radial direction, after which it is consumed. Similarly, the fuel molecule in this position has to travel like this and go to the tip when it is consumed, correct. So, fuel has to travel by diffusion in the radial direction from the central line and reach the flame surface where it is consumed. Okay. In the axial direction, from the nozzle exit, it has to go to the flame tip and it is to be consumed basically. Okay. The flame has to be steady. Please understand, the flame has to be steady. So, if the molecule which is travelling in the radial direction is slower than the molecule which is convected in the axial direction, then there will be unsteadiness here. Basically, you can see that the length is higher, the radius is shorter, just because of the scales of the diffusion and the convection. Convective time scale is lesser, so within a shorter time the molecule travels a longer distance in the axial direction, but in the radial direction due to diffusion it has travelled only a shorter distance. So, you get the shape which is like this, correct. So, in the flame radius are much shorter than the length because of the diffusion dominated transport in the radial direction and convection dominated transport in the axial direction. Okay. Now, let us take a molecule, okay, laminar regime, molecular diffusion alone is considered. So, now fuel molecule, now from the axial axis, it goes travels a distance y in the radial direction before it reaches the flame. Okay. From the axis, the fuel molecule travels a distance y, small y, before it reaches the flame where it is consumed. Okay. Now, what is this y? In the terms of molecular diffusivity, here only binary is used. For example, you can say fuel and air. So, how the rate at which the fuel goes into air also we can take. Some diffusivity you take d. In terms of diffusivity, what is the distance y it has travelled? It can be written using Einstein diffusion equation, which is also called average square displacement, which is y square is approximately equal to 2 into the diffusivity into time. So, this is actually meter square, and this will be, you can see that meter square per second and second. So, this d as meter square per second. So, Einstein diffusion equation or the average square displacement says that y square is proportional to or it is equal to 2 times d into t. Okay. So, if this is the y it has travelled, y is the distance travelled by the molecule from the central line to the flame radius, that will be equal to 2 times the diffusivity into time what it takes. We are interested in finding time again. Okay. Okay. Now, if you see this, what will be the order of distance the molecule has to travel from the axis to the flame? It is order of, see, for example, it may be higher here, it may be equal to radius at this exit, it may be higher here in the middle somewhere, and it may be slower here. So, on average what we can say is, on an average this the distance which is travelled by the molecule from the central line to the flame sheet or the flame surface will be of order of the radius of the pipe or the port, correct. So, that is, so if you see all the flames what we have depicted in these figures, in this figure, as you can see that this is the radius. So, the flame radius is almost of order of, it is not exactly equal to the radius, but of order of the radius of the port. If you have a bigger pipe, then the flame also will be, the flame radius will be at least equal to the radius of the pipe, correct. So, the molecule at the central line to the surface has to travel at least a distance which is equal to radius, correct. So, that means y will be of order of the radius. So, I do not want to take an arbitrary distance y here. So, the known value is radius, so I will take that. So, that is what I am trying to do here. So, since the distance travelled by the fuel molecule in the radial direction is of order of the burner radius, correct. So, I can say y is approximately equal to r. Okay, then use the diffusion equation, instead of y square I put r square. So, r square is equal to 2 times the diffusion coefficient or the diffusivity into t, or I am interested in time equal to r square by 2d. So, that is the time taken by a molecule from the central line to reach the flame surface, r square by 2d. Now we see this is the diffusion time scale. Now we will see the convective time scale. So at the nozzle exit, here the velocity is VE and the flame height is, okay, the flame height here is LF, flame height. So for a molecule here convectively to reach this flame height, what is the time scale? So VE is the jet exit velocity, okay, then time taken for the fuel molecule from this point to reach the flame height LF will be distance by velocity. So LF by VE, so that is the time it takes. But for the time the molecule reaches from this point here, this point to the flame sheet in the radial direction, or this point the flame tip will be the same because the flame is intact there. So you can say that R square by 2D should be equal to LF by VE, because this since the convective transport is there, the length is higher, much higher than the radius. So when you, but the time taken should be the same, you equate this. So R square by 2D is equal to LF by VE, or we can say scaling analysis, okay, order of the order of magnitude, if it is same, that is enough for us. So now LF, the flame length, is VE R square by 2 into the diffusivity. This is D is diffusivity, okay, that is it. So now what is the volumetric flow rate of the fuel? That is nothing but pi r square, area of cross section, pi r square, area of cross section into velocity. So pi, put a pi here, so r square by 2d, so pi divide multiply and divide by pi. So if I say pi and r square VE, that will be QF. So QF by 2 pi d, that will be the length of the flame, okay. So length of the flame LF is approximately equal to, because of scaling analysis, volumetric flow rate of the fuel divided by 2 pi into the binary diffusivity. So this will be the meters. So LF is in meters, okay. So now this means when the volumetric flow rate is increased, the flame height will increase. Diffusivity will not change much. If you fix the fuel and the air, the diffusivity, the average diffusivity also you can take, will not change much. So the denominator is predominantly a constant, so it has to vary. The fuel flow rate, if it is increased, the flame length has to increase in the laminar regime. So at a given flow rate in the laminar regime, the flame height depends on QF. So that is right, okay. So which may be obtained due to the different combination of burner diameter and jet flow. So QF, as I told you, it is pi r square into VE. So that means I can vary the diameter of the burner or the velocity. So by the combination of this, you can vary this. So so actually speaking, this is the only factor which is seem to be affecting the flame length. That is what we also see here in this pictures. You can see that from 2.7 liters per hour, when you increase the flow rate to 3.3, 3.8, etc., you can see a significant increase in the this. It is almost a linear increase also. You can see this. So this is what is the laminar flame length of a jet diffusion flame. Okay. So now let us go to the next topic here. So how it is controlled? See, for example, no, these flames are formed under normal gravity. We have to discuss this also. So these flames actually are formed due to, for example, you can see this, the flame shape, etc. This is due to experiments done in the normal gravity condition. But if you go to, say, for example, space and do the experiment without say microgravity or zero gravity environment, then the flame shape will be entirely different. So this type of flame shape is important to this not only because of the convection, it is also because of the buoyancy force which is there. For example, if we have a hot surface, so this is at say TH, and we have a cold ambient. So TH is greater than Tc, you can see that the particles which are in contact with this, you will have a motion like this, correct. So, you have a natural convection which is occurring. So, this is the surface which is at a hotter temperature Th, and say this T infinity is cold, then you have a natural convection driven flow. So, that also will aid here. See, then the flow rates are lower here based upon the strength of the convection. The natural convection induced flow also will be there. So, in the normal gravity conditions, both the convection, force convection and the natural convection also will play a role, but which is going to be dominant, whether the momentum of the jet is going to be dominant or the buoyancy driven flow, because the flame is hot surface, flame is like a hot surface, and when you go away from the flame, you can see this here. When you go away, you can see the temperature etc. dropping. So, here in the structure, sorry. Yeah, in the structure you can see that temperature drops from the hot condition, hot surface here, temperature drops very rapidly to a very low value. So, you can see this will impart. So, the density here will be very low, density here will be very high. So, there will be a buoyancy driven acceleration. So, the buoyancy also will be there to impart this particular shape to the flame. So, in general, which is going to dominate, whether the momentum itself is going to dominate or the buoyancy is going to dominate or both. So, if the velocity, you can literally just guess. So, if the velocity of the fuel jet is very low, then the buoyancy force will be higher than this, or maybe it will be comparable or higher than the velocity. If the jet velocity is increased, then the buoyancy force may be negligible. So, the regimes of the diffusion flame, jet diffusion flame is what we are going to discuss here in this diffusion flame regimes. So, just to give a preamble. So, which is going to control, we have to define a non-dimensional number for this called Froude number, flame Froude number, which is defined as the ratio of initial jet momentum, that will be the convective strength of the fuel jet, and the buoyant force experienced by the flame, which is due to the temperature gradient and the gravity. Okay, that is actually temperature gradient which is inducing a density gradient. So, the density gradient driven flow is the buoyant flow, buoyancy flow to the buoyancy, natural convective flow. Okay. Now, initial jet momentum is a function of exit velocity VE, and the buoyancy force is flame height itself, that is the hot surface what we have, and very near to that the cold region is there. So, due to this there will be so along the entire length of the flame we will have a buoyancy force basically. Okay. So, what is the acceleration? When there is a force, there is a mass and the acceleration. What is the acceleration due to the buoyancy force actually created on the hot gases? The hot gases rise up, correct, accelerate up. What is that acceleration? Typically, if you can calculate the acceleration, it again, as I told you, depends upon the temperature gradient and the acceleration due to gravity. If Tf is the flame temperature, T infinity is the ambient temperature. Due to this delta T only this is driven. So, 0.6 some factor g is approximate, please understand it is approximate, 0.6 acceleration due to gravity, which is 9.81 meter per second square, delta T by T infinity. I am just normalizing this. So, this will be the strength of the acceleration due to buoyancy. Okay, now, if you know this value of A, so we can say that this is maybe just taken as A. See, in many cases you can also approximately take A, the buoyancy driven acceleration, as just the acceleration due to gravity itself, that is not a problem. So, in this case Froude number will be V square by A or G into LF, that is it. So, Froude number is a non-dimensional number which is equal to V square, that is meter square by second square, divided by A into LF, which is nothing but meter per second square into meter. So, that will cancel. So, that is non-dimensional number. So, if convection is dominated, then we will see the momentum controlled regime. That means, if Froude number is much greater than 1, that means either the buoyancy driven acceleration is low or the velocity of the jet is high, then the flame is momentum controlled. Okay. because the momentum is going to control the thing, the entire flame length, etc. But on the other hand, if fluid number is much less than 1, that means what happens here, V is very less or acceleration due to buoyancy force is very high. Okay, in that case flame is buoyancy controlled. In several cases we will get both momentum as well as buoyancy force which is controlling the flame. Okay, so let me stop here, then we will proceed the next class.